modern airplane is very flexible. These motions of the structure are demonstrations induced by the pilot's intentional activation of controls. The modern airplane is a remarkable, efficiently designed structure. It must be strong enough to endure and ensure many different loading conditions, yet to perform well, it must be light. Hence, as you have just witnessed, it is inherently flexible. Now, flexibility implies that the structure will deform under load, and the deformation will modify the aerodynamic load distributions. Out of this interaction process between aerodynamics and structures, which is an aeroelastic feedback process, there arises a host of response and stability problems which must be understood and designed for in order to provide adequate strength and stiffness to ensure the control of the vehicle and the integrity of the structure. At the NASA Langley Research Center, dedicated scientists and engineers perform basic and applied research on aeroelasticity. They employ specially designed elastic and dynamically scaled models that simulate both the vibrational and aerodynamic characteristics and supplement their use in wind tunnel research by mathematical analysis. This film will display some aeroelastic phenomena and associated experimental techniques. The Langley Transonic Dynamics Wind Tunnel is exclusively devoted to research on aeroelasticity. An elastically scaled model, in this case of the F-105 airplane, is responding to gusts generated by wakes of the oscillating vanes located upstream. A suspension system should allow simulation of all important modes of motion of a free airplane. In the wind tunnel, this is accomplished by this unique Langley two-cable system. Low gust rates excite the movement of the whole airplane. On the other hand, high frequencies excite the vehicle vibrational modes. Atmospheric turbulence is composed of a continuous spectrum of such frequencies and can affect passenger comfort or structural stresses. In addition to gust response problems, there are several aeroelastic instability problems. One of these is flutter, and as you will note, flutter phenomena may be quite violent. Therefore, flutter must be avoided in flight vehicles by basic design. Now, scaled dynamic models, such as this model that you will see in the next scenes, are representative of full-scale airplanes and are tested not only for their responses below critical speeds, but also sufficiently beyond scaled flight conditions at higher dynamic pressures, for example, in order to actually reach flutter speeds, to help establish the margins of safety, to aid in flight vehicle testing, and what is also important, for correlation with mathematical analysis. The T-tail of a C-5A airplane is undergoing antisymmetric flutter. The tufts help to visualize flow patterns. Symmetric flutter here arises by a change in the stabilizer pitch stiffness. Flutter of the C-5A airplane wing indicates, obviously, that flutter must be avoided in design. Transport airplane flutter shows that many vibrational modes are interacting and need to be simulated by both model and analysis. This flutter model of an SST-type wing is unique in that its structural elements are scaled replicas of the full-scale wing and even includes wet fuel tanks. An F-14 fighter model experiences wing flutter. External stores or fuel tanks change the aeroelastic behavior of an F-111 wing to cause flutter.